Good day everyone, my name is Wishang and today I'll be presenting on the extractive distillation of bioethanol focusing on investigating an advanced separation phenomenon and parametric optimization. So to understand why we need advanced distillation, we first have to look at the thermodynamic limits of the ethanol water mixture. Ethanol water forms homogeneous minimum boiling isotopes at 89.5 mole/% ethanol at atmospheric pressure. And at this point, the relative volatility becomes 1, meaning the vapor and liquid composition are identical. And because of this rigid boundary, standard fractional distillation simply cannot exceed the purity. However, industrial fuel-grade bioethanol demands an anhydrous purity of over 99.9 mole%. To bridge this gap, we must employ enhanced mass transfer methods to alter phase behavior. So this brings us to extractive distillation using ethylene glycol as a heavy entrainer, and ethylene glycol has a high boiling point of 197.3 Celsius and is fed near the top of the column. Due to strong polar interaction with water, it selectively affects water, significantly boosting ethanol relative volatility above 1. The beauty of this approach is that it bypasses the binary boundary without introducing any new ternary isotopes, and studies actually show it requires less energy compared to classic isotropic distillation method. So to model this complex system accurately, we utilize the NRTL model, and this model accounts for local liquid composition's non-idealities, which is crucial for polar liquid mixtures like ethanol water and ethylene glycol. And as seen in our RCM, there are no any distillation boundaries in this ternary system. So the isotropic feed acts as an unstable node, while ethylene glycol acts as the stable node. Looking at the VLE volatility enhancement plot, increasing the solvent fraction from 0.1 to 0.9 completely eliminates the isotropic inflection, shifting the curve well away from the x equal to y line. And here is our process flowsheet, which consists of two main columns, extractive column C1 and solvent recovery column C2. So C1 takes a baseline crude feed of 100 kmol per hour at each bubble point of 78.15 Celsius, along with 70 kmol per hour of heavy ethylene glycol solvent. High purity anhydrous ethanol over 99.9 mole% is recovered overhead as distillate, while the bottom stream containing water and solvent is sent directly to our solvent recovery column C2. And our C2 strips the water overhead as a purified wastewater effluent and regenerates the pure, nearly pure ethylene glycol at the bottom, which can then be recycled back to our C1. And during our parametric study, we observed an interesting phenomenon, which is non-monotonic reflux behavior. And in conventional distillation, increasing the reflux ratio slightly increase the product purity. But in extractive distillation, product purity hits a local peak, and in our case, at a reflux ratio around 1. Beyond this point, an over-refluxing penalty occurs, and excessive liquid reflux dilutes the entrainer concentration on the upper extractive trace. And this drops the liquid phase relative volatility and actually degrades our separation performance. We also evaluated the SF ratio. If the solvent flow rate is too low, the isotope isn't broken, and if it's too high, energy consumption and column sizing skyrocket. Our sensitivity curve demonstrates a logarithm growth profile. Distillate ethanol purity jumps sharply up to a solvent flow rate of 70 kmol per hour, hitting the targeted purity threshold efficiently without overloading the entrainer. And also, analyzing column stage count, we observe a distinct elbow point at 28 stages. Moving from 25 to 28 stages, use a notable plus 4% jumps in ethanol purity, reaching 99.9%. But pushing further to 30 stages only use a marginal 0.07% purity gain, offering a very diminishing returns while driving up our capital expenditure. Comparing our base case against our optimized design reveals important trade-off. By optimizing to 28 stages down from 30, we save on capex, of course. Increasing the reflux ratio from 0.45 to 1 achieve a 35% reduction in overhead water impurities, hitting 99.98 mole% purity. However, operating at peak purity increased the reboiler duty by 28.7% up to 8.69 megawatts and raises direct CO2 emissions to 590.2 kg per hour. So to address these penalties, we actually propose three key sustainable enhancements. So the first, feed preheating via heat integration. So using the hot regenerated solvent from C2 bottoms to preheat the incoming exotropic feed. And this will significantly offset our C1 reboiler duty. And second, try to operate at an intermediate reflux, approximately 0.65. It still secures 99.95 mole% purity while bypassing the 28.7% energy penalty. Lastly, we try to explore short solvent mixtures or even ionic liquids to actually unlock even high energy efficiency. And thanks for watching. If you have any questions, feel free to leave them in comment section below. Thanks. Goodbye.